Today, we are delighted to have Professor from the University of France, a leading expert in superconductivity. Today, we will be discussing some of the latest advances in this field. Please join me in welcoming Professor.
Thank you for the introduction. Buenas tardes, everyone. I'm pleased to be here. Thank you for the invitation of Víctor. So I want to share some work on research activity that we did in my laboratory. So the laboratory's name is GREEN, which is not the color. It means Group of Research in Electrical Engineering of Nancy. And I mainly focus in my presentation of today on the superconductivity application. But since you are maybe not familiar with this, I will make some recaps about the application and the planning of superconductivity. So first of all, this is very common for people coming from abroad to share some specialty. So I don't bring some cheese here, but you have here a picture of the 1,000 kind of cheese we have in France. I live in what we call the Grand Est region, which is in the blue here. So it's a very big region, but in the past, it was the old region is called Lorraine. So the university where I belong is the University of Lorraine. This is the unique university in the Lorraine region, but in fact, it's a university that is on different sites. I will show you later. In terms of population and size, you can see here. So Lorraine and Nancy population on surfaces. So if I compare to your city, there are twice more residents in as Salco, sorry for the pronunciation, but in fact there are much more area. So which means we have a lot of space to welcome foreigners, Mexican students, and so on. So please come to visit us. In France, at least in Nancy, to see the beauty of the city and our costs. So just one slide on the university. So I have mentioned the university there is one unique public university in the Lorraine region, but in fact there are different sites. So two metropolises, the big city are Nancy and Metz, 11 towns and cities. And altogether, it brings to 60,000 students. So this is a big number, but in fact, split in maybe for my faculty, it is around 5,000 students, which is less than what you have here at the moment. So this is my presentation outline. I will talk first about the GREEN laboratory. Then I will change to introduce you to some basics of superconductivity. I will show you the main application right now of the superconductivity activity. And then I will give you the research field we are studying in the GREEN, mainly superconducting cable. And I think I will not have time, but there is a second topic that is related to superconducting motors. And maybe if I have time, I will share you also some application related to that. So my laboratory belongs to what we call a science cluster, EMPP, which involves energy, mechanics, and product processes. It belongs also to the Carnot Institute, which the role of this institute is to promote the research through the industry to make innovative work. In fact, the laboratory is split into 3 different locations. The main are the Faculty of Science, where I belong, and the EDSEM, which is a graduate school of mechanical and electrical engineering. People involved in the lab, we are about 20 lecturers. So most of us are both teacher and researcher. We have 8 professors and 12 associate professors, and 1/3 of this group belongs to more or less the superconductivity field, so which makes us the biggest team in France working on the application of superconductivity. Right now, there is we are hiring someone to be a junior professor, so it will end at the end of the month. So we hope we will have new people involved in the superconductivity, in particular for energy efficiency. We have two associate researchers. For example, Frederick Trio from the UNAM is part of the lab as associate professor. Yes. And we have also some technical staff and about 15 PhD students and postdoctoral students, which is not that much. This is a view of the campus. So this is my campus where I work. I mean, I live, I spend most of my time. So this is a very specific campus. Maybe it's from the 1970s. So it's an old one with a very nice architecture. And it is also a green, there are some green areas, so you can spend your time around mostly as you do here. What are the specificity of the green laboratory? In fact, the green laboratory has two main topics of research activity. The first one is the modeling and the optimization of electrochemical conversion system, so electrical machines and things like that. And the second one is related to the characterization and application of superconductors in electrical engineering. As some example, you can see some kind of device we study. This is here a magnetic coupler with a permanent magnet and asynchronous rotor. You have here a cloud type alternator that is studied for Renault company in France, so alternator in the car, for example. So we are studying this as well. And on the superconductivity application, the two examples I want to show you. So this is an axial type superconducting motors with bulk superconductor, and the stator here is conventional. And another application I would be more focused because we have a huge project in France on the superconducting cable. Concerning our expertise, so we do modeling. So modeling means a lot of things. So we do not only finite element simulation, we also do 2D and 3D analytical modeling, which means that we write the equation by the end and solve the equation with the separation variable methods. This is common for electrical machine, for example, but in 3D, the calculation starts to become more complex. We do also some semi-analytical modeling, for example, using permanence or reluctance networks. And we do also 3D finite element modeling, but we use for my part, mainly Thomson, but we have also some user of open source software as Jiménez and GTP. While we are doing this simulation and calculation, because we are doing design of optimization of devices or electrical motors or other kind of motors of converter, and we are also conducting experimental tests both for making characterization of the material, for example, of the iron sheet, of the resistivity of the material at various temperatures, but we are also building some prototype to validate and make proof of concept. So now let's switch to some superconductivity stuff. As you may know, it was first discovered, so more than 1 century before the superconductivity states. It belongs to Kévin, or at least one of his students working with him. And he discovered that below a certain, what we call critical temperature, the resistance of the material disappears. So this makes happen the concept of critical temperature. This is one concept you may know for superconductor. So superconductor has a zero resistance when they are used below the critical temperature. The second effect, which is maybe not well known, it is what we call a Meissner effect. So this is also a very special state of the superconductor. In this state, so it was discovered by Meissner. In this state, when the superconductor is cooled down, there is an expulsion of the magnetic field. So this expulsion does not appear with any variation of the field. So this is not an induced current, for example, This is a completely magnetic different state that make the magnetic field completely expelled from the superconductor. So you can see here when the superconductor is warmed, the field cross the superconductor. Just by cooling down the sample, the field is expelled from the superconductor. So this is exactly the opposite of what we have with ferromagnetic material. Ferromagnetic material, you are focusing the magnetic field. With superconductor, you are shielding. But in fact, you can have almost the same application with this effect that with iron, because you can produce a variation of magnetic field in that case. But this effect is not very strong. And in fact, there are two categories of superconductor, what we call type 1. This is a very low critical field. So usually this type of superconductor is not used in electrical engineering applications since we are reaching hundreds of millitesla or several Tesla. So this type is not useful. So we are using what we call type 2 superconductor. And for this superconductor, there are two critical fields. The first one, where there is a complete expulsion of the magnetic field. And the second critical field, where the superconductor is not superconducting anymore. It's called normal state. And in between, we call the mixed states. And in this region, the superconductor is still superconducting material, but there is an apparition of penetration that we call vortices in the superconductor. So there are some magnetic field across the superconductor. So this is the second thing you should know about superconductivity. So the Meissner effect on the critical field. I will explain the presentation that you can maybe see in the YouTube link. What you may care here is there are two different kinds of levitation. One is due only to the Meissner effect, what I showed you before. And the second one is due to the induced currents, to the Lorentz law. So this one is purely related to the Meissner effect. And then there is a third thing you should know about superconductivity. This one is quite tricky, but I will explain you very simply. If you look at the voltage current relationship of a superconductor, in fact, there are different parts in this relationship. In the first region, below what we call a critical current, but it's not very critical, there is a full superconducting state where the resistance is zero or very close to zero. We cannot measure this kind of resistance. In the second part of the relationship, we have a flux flow, which means that the vortices are moving and generating some electrical field and losses. So it is still a superconductor, but with losses. It's not a perfect conductor. Finally, we have a linear slope here in what we call the flux flow region. This one was the flux rate. And at the end, there is another, not critical, but another current that makes the superconductor completely resistive material. So this kind of curve is true in an adiabatic condition without thermal experiments, but in fact, inside the material that is not pure, not homogeneous, you have a multitude of relationships like this, which make it smoother. But at the end, the relationship that we use is something that here, the voltage is related to the current, to the power of the current at a certain exponent. So this is what we call the power law. So here, what you should know that there are some definition of critical currents, which makes the superconductor not dissipating or dissipating, but is still superconducting in this area again. So different kind of definition. All this together make that you have three critical quantities: the temperature, the critical field, and the critical current density. All these quantities are related to each other, so they are connected. In fact, it defines some surface between the three axes. Above these surfaces, the superconductor is not superconducting or dissipating. And below this curve, these surfaces, the superconductor is in the superconducting states. So you have here some example of what we call low temperature superconductor. The most known might be lithium titanium. And the more recent superconductor that is called high temperature, for example, the YBCM1. So it was just the three things I want to remind you about the superconductivity. Then I will switch to some of the application. The main application right now of superconductor is the MRI. So magnetic resonance imagery. there are more than 50,000 MRI installed worldwide, and 75% or more of these are superconducting ones. So basically, this is just a coil where you feed with currents. It should be, when it is a superconducting one, it should be short circuits, so you don't have to feed the current all the time. Since there is no resistance, the current is always flowing in the coil, and it produces a very strong magnetic field. Standard MRI are in the range of 1.5 or 3 Tesla, but there are new generation above this field. So these are the common MRIs. The MRI industry represents more than 4,000 tons per year, which makes this market the biggest impact of the application of the superconductor, and they use mostly the niobium titanium. So when you see this kind of conductor, it is very similar to a copper wire, but it's a superconducting one. And the cost of this instrument is around $2.5 million, which makes this the most expensive for clinical experiments. What you can get with MRI, you should know. So you can get very nice images of brain, but you can also have some functional images, blood flow, other kind of study. So what is related to the quality of the images of the study is the background field. So more higher is the field you use for the MRIs, more bigger should be the quality of the resolution in a certain time for the acquisition. If you spend more time, you will get a better images, but for example, in 15 minutes time, you will get better resolution when you use higher field MRI. What we have in France, so we have at the moment the world records for the more powerful MRI for human images since 2019. It's 11.7 Tesla MRI. I just heard a couple of weeks ago that they make the first brain images of this, so you can find some picture on the website. And this is the schematic view of the MRI. So basically, it's a coil, superconducting coil, cooled down in a vessel, and at the end, it looks like a huge piece of stainless steel mostly. But now there are some other equipment around, so it looks more or less like a conventional MRI. But behind this is how it looks like. Another application that is almost the same as the MRI is called NMR, but the application is not the same. For NMR, nuclear magnetic resonance, we are using almost the same physics behind to make 3D analysis or non-invasive analysis of structure. So it is used in biology for studying the molecule or the protein. It is used also in the chemical industry, in the oil industry, and in the pharmaceutical industry. The size of the bore of the experiments you are targeting is very smaller compared to the one you need for human bodies. So this is why you can reach higher magnetic field. So this is the highest NMR produced by the Bruker company, one of the leaders in the field. So the field here is 28 Tesla, and it's related to the resonance of 1.2 gigahertz. So in fact, when you are using NMR system, we are more talking about the frequency, but behind there is a relationship between the field. And again, this application on field is related to the quality and the time we spend to make the experiments. So higher is the field, you will get higher resolution in a certain time. So this is very convenient, in particular in some industry here. Another kind of application, but it's still a huge one. This is what we call the family of the large-scale instrument for physics. One of the largest one is the superconducting collider, the Large Hadron Collider in Switzerland, but also there are some parts in France. The LHC push the proton near to the speed of the light. So you have the right value here. But in fact, it is a circle with a lot of magnets. Most of the magnets are used to bend the particles. So this is what we call the dipole magnets. And all these magnets are superconducting one. So for making this 27-kilometer loop, you can imagine the amounts of superconductor they use. So this is also used a big user of superconducting material in this field. In fact, so this is a loop of the LEC to accelerate and bend the particles. But there are also some very specific instruments. For example, the CMS on the Atlas one at some location of the loop. The goal of these two instruments are to detect very special particles like muon, for example. Both are the same goals, but they are not using the same technology. For example, Atlas is a toroidal superconducting coil. So the length of this is typically like more than 6 or maybe 10 meters long. And you can see this is the toroid. So this is one, not one term, but several terms. It's a discrete toroid. And these are the wire of this toroid. And on the other side, the other experiment is the CMS, which means compact solenoid for muons. It's also used a very big superconducting coil. So these are other applications you can find in the field of physics large-scale instruments. The last one, but it is also maybe the future for superconductivity. This is the application that is targeted for the fusion application. For the fusion application, the process is to make fuse two light atoms to produce energy. At the moment, the record of produce energy versus the energy you use to produce this plasma has been recorded by the Joint European Torus experiment, JET. It's a non-superconducting tokamak, but it has to be mentioned because it has the highest, what we call the fusion power coefficient. So when you are above 1, it means that you create more power than you use to produce the fusion of the atom. So at the moment, this is the record. What we have in France, but in fact, it is an international project. It is called ITER, International Thermonuclear Experimental Reactor. So it starts in 2006. It is still under construction in the Cadarache area. So this is close to Aix-en-Provence, Marseille, in the south of France. It is designed to yield in a 10-fold return of power, which means Q equals 10, or 500 megawatt of power for 50 megawatt of power as inputs. There are other kind of fusion reactors. We should mention the Japanese one, JT60SA, which is smaller than ITER, but the goal is to use other particles to study, for example, hydrogen, and later deuterium instead of the tritium that is used for ITER. And after that, we are already thinking about a demonstrator for a power plant fusion reactor. The project is called DEMO. In this project, the goal is to reach 2 gigawatts of power for only 80 megawatts of input power, which means a coefficient of 20. But first, we might focus on the ITER one, because this is a very challenging project right now. You can see here a different size of the different tokamak. So ITER is nearly the biggest one up to now. It's maybe the major radius should be around 6 meters, but the length is more or less 13 meters high, something like this. And you have the jet experiments, so the copper, the classical one, and the GT60. The superconducting magnets represent 50% of the ITER budget, so this is why this is an important part of the application of superconductor. And it represents 20 billion euros, for example, but this is maybe not accurate numbers. It increased with time, but the number I get, this is what we get. So in the ITER experiment, you have in fact three different kind of superconducting coils. What we call the TF means toroidal system. So this is a part of the toroidal system, which makes the field circulate inside the toroidal system like a donut. Secondly, there is what we call the PF is a poloidal system, which makes a field turn inside this area. And the combination of these two fields create the confinement of the plasma. To make circulate the plasma, you need a transient variation of the magnetic field that is achieved with a solenoid, central solenoid system at the center. So this is a pulsating magnetic field that creates induced current in the plasma and make it reach a very high temperature to make the fusion possible and get the power in this field. So this was the main application I want to share with you. Maybe you know some of them, maybe not all the numbers. Now I will switch to what are the other promising applications we are studying in my laboratory. So and first, I will show you some application related to HTS, mean high temperature superconductor. So since the discovery of what we call high temperature superconductor in the 1986, and with the revolution of the cooling system, which appeared around 2000, there are new applications in the field of electrical engineering. So I will mention some of them. There is no special meaning of the order, but firstly, the superconducting magnetic energy storage, which is similar to what you get with a capacitor, but with the magnetic field. So in a capacitor, you may know that you can store the energy charging with the voltage. In a superconducting storage, you store the current. And since there is no resistance, the current is storing all the time. So you have a negative storage, which was not possible with classical conductors. Another kind of application is a superconducting fault current limiter. If you use the fact that the superconductor may switch from the superconducting state, which means low resistance, to the normal state, which means high resistance, you can have a system that can, in case of high currents in a short circuit, for example, you can reduce the amplitude of these currents by making the apparition of high impedance or high resistance, and then you can decrease the peak current. So this is what we call fault current limiter when using superconductor. You can also think about another kind of application, just replacing the copper with superconductor. So superconducting machine, superconducting transformer, everything can be superconducting, but you need to study if there is a gain in the efficiency, including the cooling system, for example. So the two main topics we are studying in the Green Laboratory are, as mentioned before, the cables and the motors and generators using superconductors. Why superconducting cables? Of course, it was thought many years before, but now we are reaching some capacity limits, or we need more and more energy. If you are thinking about the size of the corridor that you need to transmit like 3 or 5 gigawatts of power, you need either a very high pillar, electrical pillar, a very huge corridor, or you need to make a lot of civil engineering work to make this possible. So these are conventional cable, and this is an example of how to transmit this bulk power. If you look at the comparison for a 5 gigawatts power with the high voltage buses, so this is an example of a three-phase system on the corridor, which is more or less 600 feet wide. For the same amount of power, you just need a 3 feet diameter pipe using superconductor. So you can see the gain in the time of the size of the system. This is another example, but the same conclusion for typically for a DC cable used in the highway network. To have a 50 kiloamp cable, you need to split the cable in different size and different smaller core. Typically, these are 400 millimeter square cable, and replacing this, you just need a 20 square envelope to make this possible with superconductor. So this is very interesting application in urban and dense area. So this is why we are studying this right now for the project I will told you right after. So what are the benefits for the superconducting cable? Higher transmission capability at lower voltage, higher transmission capacity at lower diameter, It's no ground heating because it's inside the vacuum cryostat, which means that there are no thermal emission from the cable. There is no electromagnetic emission because the magnetic field is shielded inside the envelope. And most of the material used are 100% recyclable. In terms of operation, we can have a return of costs in operation since we have less losses. But again, we have to calculate that including the cooling system, which the efficiency is still not that good, you know, the Carnot efficiency of cooling system. So in some cases, there is some interest in terms of money, but this is not always the main argument or the main benefits of superconductor. I want to show you different kind of superconducting cable. So these are three different layouts of a three-phase cable. I will start with the one on the right. So on this cable, this is a three-phase concentric cable, which means the three phases are coaxial. There is a kind of asymmetry in this cable, but the goal is to make it more compact. This is possible because the voltage used is not so high, so the dielectric material is very thin. In other case, so in the range of 30 to 100 kilovolts, you might split the conductor in three different cables, but all these cables belong to the same cryostat, so they share the same liquid nitrogen, the same coulomps, and they are sharing the same cryostats. At the end, if you go to higher voltage, for example, higher than 100 kilovolts, you need to split the three-phase cable into three cryostats, three cables, because the thickness needed for the electrical insulation is bigger. So it is more efficient in terms of cooling, in terms of capability to split in three different cables. This is the review of the project since 2001. The orange dots represent the AC cable, some prototypes. This is the transmit power against the length. And the blue square are the DC prototypes. So at the moment, there are less DC prototypes than AC cable because AC are used for transmitting the power. But we are using DC cable because for highway application, they use DC and there is a huge benefits for using them. So this is the project we are involved in France with another group and colleague. The project name is called SuperHigh, which means superconductivity for highway. And I will show you the goal of this project. So in the Montparnasse station, you might know there are maybe 4 big stations in the Paris area. Montparnasse is one of them. In 2008, there are a huge fire due to the electrical substation that reached its capability. So there is a need to improve the electrical installation of the SNCF network, for example, in this area. And it was not possible to reinforce the electrical station or the capability with conventional copper because there is no place anymore available. So what we propose in this project is to use superconducting cable to take the benefit of the size. So this is part of the roadmap of the SNCF that is in the 10 years range, 2025 to 2035. Right after the Olympic Games, they will make huge efforts to make more power available and more train available for Paris passengers. The project, the consortium is made of the network operator, SNCF. There is just one big operator in France. 2 industry partners. Nexans is a cable manufacturer worldwide now. It produces copper cable, aluminum cable, but also superconducting cable. There is a manufacturing now in France for superconducting cables. And the second industry is the absolute system. It was a startup, but now it's more or less like 100 people working there, and they are specialists in designing the cryogenic system or the cooling system for the cable. Apart of that, we are 2 research labs, so Central Superlake and the University of Lorraine, where I know. So what are the several objectives of the project? So as mentioned before, to increase the energy density and to make more commercial offer for the public transportation and more reliability to avoid stop in the transportation and things like this, or incidents as the fire as mentioned in the Montparnasse. The second objective is to develop the industry and the education related to superconducting cables. So in my university, at the master level, we teach superconductor. We have some practical experiment on superconductor, but this is not widespread in France. We also want to deploy, so this will be the first commercial demonstrator in long-term application of superconducting cable. There are some prototypes in Japan, but they are not in operation, all the time. Just some prototype. And it's also to validate the technology, because there are other cases in Paris where we can use this kind of solution to improve the energy of the network. These are some picture. So this is the Paris, central Paris. This is the location of the Montparnasse station. This is the highway track that belongs to the Montparnasse station. And this is one of the substations that is called Vouillet. So the electrical substation that feeds the currents to the substation. I think it's a 6.6 megawatt substation. And between this substation that could somehow find a hole, but there are some electrical equipment behind. We will make a connection from this to the highway to improve the capacity of the track. So on the left side, this is the duct already used by the 400 millimeter square cable. So they are almost all filled with a cable that's used for the current for feeding the train. In fact, there are only 2 remaining ducts. So there are with these ducts, and according to the fact that one cable can operate 500 amps in a permanent operation, this is not possible to make more power, except if you make a lot of civil engineering on this bridge, which is centurial and which is just below the track. So in fact, it was not a good bet to try this solution, and this is why the superconducting, the super high project are built. We will place the cable in the 2 remaining ducts here. So there is no need for civil engineering, just using what we have, and this is sufficient to pass through 1,000 amps to the train. So these are the specification of the cable. So in fact, it is not one cable; it is 2 cables. The rated current, so the rated voltage on the SSNet network is 1,500 volt DC. And the rated current is 1,500 amp. But in fact, due to the acceleration of the train, at some times during a few seconds, maybe minutes, the cable must be capable to transmit 3,500 amps. So this is why the critical current of the cable should be higher than this value. The return of the current is not made in the second cable or in a coaxial way. The return part of the current will go through the rail and through the ground. What is very challenging for this cable is it needs to sustain a short circuit about 67 kiloamps during 200 milliseconds. And this is very challenging because during these short circuits, you need to maintain the electrical insulation. You need to maintain that the cable is still operating. At least the temperature does not increase so high. And what is very challenging, you need to avoid to heat the liquid nitrogen to make bubble. Because if you have bubble in the cryostat of the cable, then you lose the electrical insulation. The electrical insulation is made of 2 parts. There are some craft paper between the conductive part and the other plate, on the other conductor, but it is mainly due also to the liquid nitrogen. So if you have some bubble somewhere, you will lose the electrical insulation. And finally, the cooling system that is quite new. it must ensure a high reliability, high efficiency, and a variable cooling to make it, for example, functioning at low power when there is no train on the track, so no need of cooling power. But when the train starts, for example, at the beginning of the day, you need to be able to produce more cooling power to cool down the cable efficiently. So the cooling power is around 1 kilowatts at 67 Kelvin. So 67 Kelvin is the temperature you can reach with liquid nitrogen. Liquid nitrogen is 77 Kelvin at atmospheric pressure. If you make the pressure decrease, or if you make subcool, what we call subcool liquid nitrogen, you can reach this. I think below 63 or 65, you have frozen nitrogen. So this is the margin between the solid state and the liquid state of the nitrogen. Here are some picture of the layout of the cable. So as you have shown you before the picture, this is the relay substation with some electrical equipment here. These are the track on the platform. Some equipment like the termination will be placed here. And this is the path of the cable. So this is 60 meters for the two cable layouts. This is a picture of the cable. So there, I show you later some maybe a different picture. What is specific here? In this part, the copper. In a conventional normal operation of a superconducting cable, you don't need copper because the current goes through the superconducting material. But here, since we need to reach this high short circuit current, 67 kiloamp, you need copper, because with these high currents, the currents here on the resistance of the superconductor will be too high, which means that the currents will through the copper core in the center. So this part is only designed to sustain the short circuit currents and to avoid any heat in the cable itself. It has, in fact, two layers of superconducting tape. So a tape, a superconducting conductor is usually as the shape of a tape. So it's not a round wire. And you can see here the agency of the two layers. So at the end, we have a total of 25 conductors. Typical width of the conductor is 4 millimeter, more or less 4 millimeter width, and 1 millimeter thick. So this is the typical size of a superconducting tape. Again, this is the layout, and this is a view, a very technical view of the termination. This part is very technical because, in fact, when you cool down the cable, you have some contraction of the material, and when you have tens of meters or maybe hundreds of meters, this contraction due to the cool down may reduce the length by a few centimeters. So this system has to be able to compensate the variation of the length. Typically, it is placed on something that can move, so we can compensate the length of the cable during the contraction. And you can see here the connection plate to the room temperature to the conventional cable on the outside. This is a view of what we call the cooling system, and the topology is a turbo-Brayton cycle. And in fact, here it is called a reverse turbo-Brayton. So this product has been completely developed by Absolute System because there is no product in that range of power. So I mentioned before, it is 1 kilowatt of cooling power. So what are the power on the application at the moment for a cryogenic system? There are a lot of applications for space, but the cooling power is a range of watts, tens of watts. And there are a lot of applications for very big industry. And in that case, it's tens, hundreds of kilowatts. In the middle, there is no commercial product available. So this is why they develop a new one with some functionality. For example, you can tune the power from 30% to 100%, and this is not possible with other cycles. So this turbo-Brayton cycle offers the possibility to tune the power, and this is also a more powerful and a more reliable system. This is the complete view of the system. So starting from the high on the train, you have the substation side. You have the two termination on the substation side and the two termination on the platform side. In fact, the two cables are electrically fed in parallel. There is no relationship between the currents, but the loop of the cooling system is in series. So which means you start with a cold liquid nitrogen here. The nitrogen will warm up with the heat during the length over the cable. There is a need for a circulation pump, so you need to have a certain mass flow of liquid nitrogen to reach the performance of the cooling. And what makes the cooling system is in fact a kind of exchanger. Here it is the reversible Brayton. So you start with one nitrogen, and then it cools down the nitrogen, and again in a closed loop you have a circulation of liquid nitrogen. So there is no need to refill. You need at least one tank of liquid nitrogen for the beginning to fill the cable with something. And in case of an emergency, and in case of if you lose the liquid nitrogen for so many reasons, it's good to have some liquid available. This is the picture not of the full cable. This is a 30-meter cable, a prototype that has been tested at the SNCF Highway Agency. In fact, last week the test was carried out, so now it's done, and all tests were successful. So firstly, we did some bending tests because there are some critical bending diameter for the cable. We did some pressure on thermal tests because when you have a huge elevation of temperature, it produces a lot of pressure, and you need to be sure that the cable and all the security equipments will sustain a certain amount of pressure without breaking. In that case, I think it is 12 bar. At that time, there are some security equipment that will open the system. We did some critical current tests to make sure that the critical current is above the 3,500 amps. We did some lightning impulse on direct tests. These were also okay. And finally, the most difficult test was the fault current limiting test. So we cannot reach the 67 kiloamp. So to make a fair comparison, instead of making this kind of current during 200 milliseconds, we do a lower current, but for the same amount of energy for a longer time. I think it's more or less 280 milliseconds. In that sense, you know that you produce the same amount of heat in the cable, and you can pull the cable in case of a short circuit. I'm almost done. I want to share what we do in the lab related to this project. So all what you see before, the cable, the cooling system, is more or less belong to the SNCF, Nexans, and Natural System Company, because this is very technical. They need to manufacture things. But what we do on the academic part, as a researcher, we make some study and we are developing simulation tool for superconducting cables. For example, in this paper, we study how a superconducting cable behave in a highway network. So we integrate the cable with a Simulink network. So it's a shared finite element simulation with Simulink. The finite element simulation we are dealing with take account the magnetic field, the currents, and the temperature, because as mentioned before, these three quantities are related to the state of the superconductor. So if you don't calculate the temperature or the magnetic field, you cannot be sure that you don't reach the critical state of the cable, for example. In this particular case, for the application of the super high cable, there are a lot of margin because the industry and Nexans wants it works fine. Maybe it's 15% of margin. But if you think about in the future application, when you need to take account the cost of the superconductor and so on, you need to optimize everything, and the margin has to be reduced maybe like 20 or 10%, because it costs at the end if you put more superconductor in the cable. And also, a part of the SNCF agency on the cable, we are developing our own platform of tests in the lab. So with this platform, we are able to feed 9 kiloamp in DC currents or low variation current to simulate the acceleration of the train. And this will be able to carry out a lot of tests on not a prototype of tape or a small cable, but on a real size cable of a few kiloamp. And this is an example of result of what we get making some simulation in other paper. These are the voltage and the current in the train. So typically here, each pipes represent an acceleration of the train. So when you have an acceleration, so there is a huge amount of power. In fact, the voltage on the train level tends to decrease because of the Joule losses across the conductor in the normal case. In fact, so this is related to the peak of current. So you can see here, when you are dealing with a DC current in a highway network, in fact, it is not DC. If you show this to students, he will not say this is a DC current. So this is a low varying current, but in fact, the network is called DC. And when we show with this simulation, so this is the total losses in gray for a conventional cable. So for the high, for the line, and in total. And we studied 2 cases of cable. One cable is unipolar, which means the current goes through the cable and go back through the high. And the second case, the HTRC, is a coaxial cable. So the current goes through the cable and back through the cable. And you can see the what we can get from the energy saving. So it is a range of 20% to 30% on the unipolar and bipolar case. So these numbers are just the losses without taking account of the efficiency of the cooling system. So this is not fair. If you take account of the cooling system, what you need to cool down and to make the pump or the circulation pump or so on circulate the liquid nitrogen in the system, we still have a gain in efficiency, and the range is in the order of 30% for the unipolar cases and 25% for the bipolar cases. These numbers are obtained for kilometers cable. For cables that are like 100 of meters, you cannot reach the number. This is only possible for high power cable, high length cables. Otherwise, there is no gain on the efficiency. So in the case of the super high projects, it was another reason why we choose this, because of the space. But there will, I think, we will see that I think there will be no gain on the efficiency. I think I'm done. I will split the machine and I will leave time for some questions. Thank you very much for your attention.
Any questions?
Even in Spanish, I cannot understand. There is the translating.
Recently, China has set a goal for strongest magnetic field ever created. It was around 135 Tesla. If I'm not wrong.
Yeah.
They use a hybrid magnet.
Yeah.
Using superconductors and a conventional electromagnet. Can you explain why they do this?
I think in this case, the field in the range of 100 Tesla is pulse mode, right? Or it's static field. Usually, yeah,
I think so.
So
Like
yes, in a peak. So there are similar experiments in the Toulouse National Magnetic Field Laboratory. So in a pulse mode, there is no really difficulty to reach high magnetic field. You just need to be able to sustain the huge mechanical force. So they use typically some composites. I didn't know they use the superconductor in that case. The one I know they don't use. But on the side of the DC magnets, there are some what we call hybrid magnets. But the field is in the range of 45, 46 Tesla. That is. So the record will be at Tallahassee at the moment, I suppose. And it's a hybrid superconducting magnet. So since the superconductor used in this kind of application have some limits in terms of magnetic field, they use a combination of huge magnet to produce a very big magnetic field with the copper, and there is an insert with superconducting cable to reach another range of magnetic field, decreasing the size of the board. At the moment, the record is 45, 46.
Anything else? In your presentation, I think so 22, that you would on just like they use in the machine about it.
Yeah.
Well, I think so you don't say for that becomes clean. How would you blame
For the superconducting machine, or for the 22 is for the fusion?
for continuity of the machine?
Okay, for the machine, I will go to the slide I didn't share with you. I have some, maybe the last one. So here's an example of prototype we developed in some projects in our lab. So it's called a resume, which is a realization of a superconducting machine. In this kind of machine, there is two parts. One part is the conventional copper you can see here. So it's an axial type machine with an iron shield, very thin iron, back iron. So this is not superconductor. The stator is conventional. Where we use superconductor is the yellow coil here. So the yellow coil is used to produce a very strong magnetic field. So in that size, we can produce a 2 Tesla background magnetic field. There is no need for iron, just using high currents with a good superconductor at a certain temperature, so we can produce this field. And the dark pellets you see here, it's what we call bulk superconductor. It's a superconductor, pure ceramic. And with this material, when they are cooled down without magnetic field, due to the Lenz's law, if you apply the variation of magnetic field across this, they will expel the magnetic field. So if you look at the variation of the magnetic field on the circumference of this, in fact, you have something similar to a permanent magnet machine. So there is some places. So these parts belong to the superconductor. On the top of the superconductor, the magnetic field is almost zero. Between these two parts here, where we use G10, G10 is a non-magnetic material, there is a magnetic field. So this creates a variation of magnetic field that is used for making electrical machine. And using superconductor, you can reach either very high magnetic field without iron, which means the machine is lighter. And even if here the value is not very high, it was due to an optimization for the special application of this machine, which is targeted for aircraft application. So the goal was not to reach very high number of field, but to make the machine lighter. The power to mass ratio was the goal here. And with this machine, later on, we make an improvement. So this is now. So we change some part of the design, choose different kind of bulk material, a second generation of superconducting material for the coil, which produce more field. The armature, in this case, is cooled with, I think it's maybe water or maybe oil. So it's a cool stator, but still conventional one. And this is at the end, the target value of the machine. So the first prototype, it was a 50 kilowatt machine. The active part was 60 kilograms, but in total, we had a lot of other material, not active, 50 kilograms, which made the power to mass ratio about 3 if you are going for the active, but just 1 kilowatt per kilogram altogether. With the new prototype, we wanted to reach a 2 kilowatts, 260 kilowatt class machine. We make a lot of improvement on the active parts. There are still work to do on the non-active parts, but for the active part of the machine, the power to mass ratio is very good, so 12 kilowatt per kilogram. Of course, the goal of the aircraft company is to have a 20 kilowatt per kilogram. Every number which is higher is better. So you need to sell good numbers for them. So this is good number to sell. In reality, this is a little bit less. But we are making prototypes on developing such kind of machine. This is part of a collaboration with Safran, which is a manufacturer for Airbus, for aircraft. And absolute system, the same I mentioned before, on our lab.
You got some tests for current simulation?
Yeah, simulation. So simulation we have, and the test will be carried out in June, I suppose. So the machine is being assembled at the moment. So it will be shared in the community later.
Carlos, the very beginning of your presentation,
Yes.
I think from slide number 10, you mentioned the areas of expertise,
Yes.
and one of them is related with optimization.
Yes.
So can you mention some examples in which you made optimization, please?
Okay. So it is not the work I'm working with, but for example, for this machine typically used since decades in the car automobile industry. So it's a global type machine for alternators. So the team working on that, they are building both 2D 0.5 model, 3D model to improve the computation cost and to make optimization of the size to make the machine more efficient, lighter, but for application. But the optimization are in the range of a few millimeters somewhere, At the end, you gain some percentage of the efficiency. This is kind of optimization we can do. So to do a lot of study on optimization, you need to have both accurate model, but also fast model. So this is why we are mixing different kind of formulation, both analytical, hybrid, something like this.
Go ahead.
This is a pure optimization in that case, because this is the request from the automobile industry. They need to make we don't change a lot of things, but make it better.
Kévin, if you want to control superconductivity electrical machine,
Yes.
About your mathematical model,
Yeah.
There are a difference.
Yes, there are difference.
Like conventional.
Yes.
Electrical.
Yes, there were one project maybe less than 10 years before. It was the EcoSwing one. It was a huge wind farm generator, and they get a problem on the power electronic side because the converter at that time, I think they do not use a special one, so they use just a conventional one. What can appear with a superconductor, since you have basically zero resistance, this is not good for stability of the network. So you have to think differently, maybe different converter to use in combination with the machine. Maybe the command law should be different. I'm not specialized in this, but for sure there are some fields to do in this area.
But it's more difficult.
I think it's not so more difficult. It's not so widespread and so not so studied.
Okay.
So some work has to be done in this direction.
Hi. I understood that this technology uses DC source for work, yeah? But the challenge about the use AC source,
Okay. So
yeah, was
yeah. So in fact, for superconductor in DC, this is the perfect form because there is no variation of field, so there is no losses or less losses. So most of the application we use, for example, the machine we design, we try to use the most static field or DC currents. But there are some application of AC cable. In that case, what you have is just it's possible to feed the cable with a lot of currents. But since you have some losses, you need to take some margin to increase the size of the conductor to be far away from the critical currents. Because when you get closer to the critical current of the tape or the cable, the losses will be bigger. In the frequency of 60 or 50 Hz, it's manageable. In the frequency you can reach in some machine, 100 Hz for harmonic and so on, it gets more complicated. So you need to take some margin, which make the system bigger, more costly. So at the moment, there are still some study to find an optimization on the configuration of the tape to get less losses. The point is the losses in AC, to reduce the losses.
One questions?
I have a question more related about thinking in plants and the benefits of superconductivity. How much CO2 emissions can you have reduced using this new technology?
I don't have this number. I don't know. Okay. Frankly speaking, I don't know any number about the CO2 at the beginning in that sense. Yeah, it should be done right after, at the end of, so the project supply will belong until 2025. At the end of the project, we'll make a return of experience. So we will see if there is an economical benefits or no, something like this. So this is part of the central superconducting work. Maybe we will say something about the CO2 and all kind of things, but for now it is too early, and I'm not specialized in this.
Yeah.
Okay, the last one, Professor Cantero. The machines are still DC or LDC?
So the machine is a synchronous machine. So the rotor is like a DC field, but the rotor is a three-phase system.
DC.
On the rotor side, yes, but on the stator side, this is the AC three-phase system.
So this.
But the rotor, the stator is a conventional one at the moment. So it's the rotor is not superconductor. You can see the picture here. This is this wire. So this is this wire on the G10 jacket. It's cool. It's cool with the oil or water. I don't remember. But this is a conventional wire, copper. But there are some other kind of machine with fully superconducting when they use both superconductor on the stator, so with AC losses, and superconductor on the rotor.
Okay. In the stator are AC loss. Simple.
There are a few, since we have some air gap in between, the field is not so, there are not so many harmonics. So most of the losses, since we are using huge magnetic field, most of the losses come from the stator armature. There are some induced currents in the coil, so this is why we use these wires as well.
Well, if there is no problem, the last one, David, go ahead.
I have known about that kind of machine that it use permanent magnet. The word rule of law it is only change the permanent magnet with
It's not exactly a change. Yeah. So it's a synchronous machine. So you need to have a variation on the rotor side of the DC field. So it's not exactly what we call a cryocopy for replication of the machine with permanent magnets. So for a synchronous machine, you need to have this variation of magnetic field. What we are using here, it was a new design by using what we call the shielding effect of the superconductor, more or less what I showed at the beginning, the Meissner effect, the expulsion of the magnetic field. And since this material can expel fields in the range of 10 Tesla, so you don't have a permanent magnet that can produce 10 Tesla. So with this, you can produce with the coil around in the middle 10 Tesla. On these parts, you will shift the 10 Tesla. So you have a variation 0, 10, 0, 10. So you have a huge variation of magnetic field, which makes the machine more efficient because the torque and power is related to the magnetic field.
You use it then as a spring.
Yeah, in this case, there are different kind of use. So you can use as a spring, but there is another kind of operation. So first, you use the background coil to produce a magnetic field. So the field applied on the bulb, for example, will be like this. You can imagine 5 Tesla, for example, which is a reasonable value. Then you pull down the bulb. So at that time, the bulb becomes superconductor. And when you will decrease the field to -5, so you start to 5, you go to -5, the superconductor, due to the Lenz's law, and is able to generate a lot of currents, it will maintain the 5 Tesla. So in that case, you will have +5, -5, +5, -5, which is with a no DC value of the field, which is better. So in that case, we will use this kind of configuration.
Thanks.
Kevin, there's
Yeah.
another question from Frederick.
Yeah,
He told me the hard
yeah,
one.
it's a very, very tough one, and you will see where it comes from. Where? Yeah, can you go back to the circuit, you know, for the railway, where you see the trains? I
Yes.
don't remember the side number. And and you will know exactly what I will ask you, I mean, when I will ask you.
This one?
Yeah, this one.
Okay.
You have the connection to RTE, no?
Yes.
Which is the CFA.
Yes.
I remember in the meeting, there was no explanation why we have a delta Y connection. Do you know, did you get that
Yeah.
information at the end? Because Carol was saying,
No,
this is back in the days, nobody knows
I
why.
know this kind of transformer, this is what, this kind of shape, right?
Yeah,
Yeah, so this is what we call the 12 pulse transformer, and this is used to reduce the ondulation on the DC side. So there is no that much filter right after. So the DC is, as you
So
have seen,
that's
sometimes
for
like
the harmonics.
3% of harmonics.
Yeah.
I have some picture to share, but not here. But this is a 12 pulse rectifier. So this is the typical configuration in that case.
Yeah, good job.
Not so hard.
Not so hard.
Well, we have one question from the people connected online. It's from Andy López. Just the past week, you made experiments and was successful.
Yeah.
What next?
Well, next, so we need to install the cable, but for the moment, there is a, how to say that? The SNCF cannot do any change of the network starting from now to the end of the overlapping games and parallel games. So we need to wait at least September or October to place all the system on the Montparnasse and Railway track. At the moment, there are already 2 terminations that are installed. These 2 ones will be installed on the platform side, but this is not possible to place them on the platform right now because they cannot make this kind of implementation with the current on the right. And what it is not also completely finalized is the cooling system. So in that experiment, they reached the optimal performance for the cooling system, but it needs to be installed close to the Bouillet substation. There is a huge platform to be done because this is a system that maybe the weight is around 8 to 10 tons. So this is a very huge system. There are not that much complication for the superconducting cable, but for the cryogenic one, there are some civil engineering at least to do.
That's all. Thank you, Professor Kévin, for your insightful talk today. And on behalf of everyone here, we present to you this token of our gratitude.
Thank you very much.
This one from around Mondragón. Thank you.
Yeah, thank you very much.
For your attendance and see you at the next event. Thank you very much. Hay café de ese lado, que puede pasar.